Hello everyone, my name is Narayan Bhute. I have recently completed my internship at Emertxe.
My embedded system internship at Emertxe, and in this presentation I will be explaining the concepts I learned and my project title microwave oven control system implemented using a PIC microcontroller. Introduction. During this internship I gained both theoretical and practical knowledge of embedded systems. In this presentation I will first explain the fundamentals such as C programming and embedded system basics, the microcontroller architecture, hardware interfacing concepts, and finally the implementation of my microwave oven project. Introduction to C programming. C programming plays a very important role in embedded system. It is called a middle level language because it supports both high level programming and low level memory access. This makes it suitable for controlling hardware directly, which is required in microcontroller based systems. C programming basics. In this internship, I learned the basics of C such as data types, operators, loops, and conditional statements. I also learned arrays and other operators like the ternary operator and size of operators. These concepts form the foundation for writing embedded C programs. What is an embedded system? An embedded system is a system designed to perform a specific task rather than multiple general tasks like computer. It is usually embedded inside larger devices such as microwave ovens, washing machines, or cars. It combines hardware and software to work efficiently in real time. Types of embedded system. Embedded systems are categorized into standalone, real time, networked, and mobile systems. My microwave home project is mainly a standalone embedded system, and it also has a real time characteristics because cooking operations depend on accurate timing. Components of embedded system. An embedded system consists of a microcontroller, memory, input devices, output devices, power supply, and embedded software. The microcontroller processes data, memory stores the program and data, inputs like switches or sensor provide information, and outputs like LCD or buzzer shows the result. What is a microcontroller? A microcontroller is like a mini computer on a single chip. It has a CPU, memory, and input-output ports. It reads inputs, processes them based on the program, and controls output accordingly. Components of a microcontroller. A microcontroller includes a CPU for processing, flash memory to store the program, RAM for temporary data, input-output ports to connect external devices, timers for time-based operation, and communication module. Types of microcontrollers. Microcontrollers are classified based on word size like 8-bit, 16-bit, and 32-bit, based on architectures such as Harvard and von Neumann, and based on application as general purpose or application specific. Development tools. For this project, I used MPLAB IDE for writing and debugging code, the XC8 compiler for compiling programs, and PICSIMLab for simulation without using any hardware. Microcontroller overview. Here we are using PIC16F877A microcontroller. It is a 8-bit microcontroller. It has 14 KB flash memory, 368 bytes RAM, and 256 bytes EEPROM. It contains 33 input-output pins and peripherals such as ADC, which is analog to digital converter, USART, which is universal synchronous asynchronous receiver and transmitter, SPI serial peripheral interface, and I2C, which is inter-integrated circuit. And the last is PWM, which is pulse width modulation, and it contains three timers, and its operating voltage is 5 volt and clock up to 20 megahertz. Advantages: it is low cost, easy to program, and very versatile. In this part of internship, I learned how to interface LEDs with the microcontroller, and an LED is connected to an output pin, and by sending high or low signals, we can turn it on or off. This helps me understand the concept of digital output and how microcontrollers control external devices. Switch programming. I also learned how to interface push buttons or switches. Switches are connected to input pins and the microcontroller reads their state as high or low. I learned about switches debouncing, which prevents fast triggering due to mechanical noise. The concept is important for reliable user input. Matrix keypad interfacing. A matrix keypad consists of buttons arranged in row and columns. When a key is pressed, it connects a specific row and column. The microcontroller scans row and columns to detect which key is pressed. This method reduces the number of input-output pins required and is used in my projects to enter cooking time and select mode. Interrupts in embedded systems. Interrupts are signals that temporarily pause the main program to handle urgent tasks. When an interrupt occurs, the microcontroller executes an interrupt service routine and then returns to the main program. Interrupts are useful for handling events like button presses or communication without continuously checking in the main loop. Timers in embedded systems. Timers are peripherals that count clock pulses to measure time. They are used to create delays, generate periodic interrupts, and perform time based operation. In my microwave oven project, timers are used to implement the cooking countdown. Peripherals used in my project. In my project, I used matrix keypad for user input, a 16x4 LCD for displaying information timers for countdown control, and a buzzer to alert cooking is complete. Project overview. My project simulates the working of a microwave oven. The user can select cooking modes and set cooking time using a keypad, and the microcontroller controls the process. Project features. The system supports cooking mode selection, time control, real-time countdown display, and buzzer notification after completion. Project workflow. The system powers on, the user selects a mode, then sets cooking time, the timer counts down, and once it's finished, the buzzer alerts the user. Now I will demonstrate my project. This is the MPLabX IDE tool which I used to write my code and debug it. Now let's move on to the PixSim Lab Simulator. This is the PixSim Lab Simulator. We first select the board, then microcontroller, then change the clock frequency to 20 hertz, 20 megahertz, then LCD to 16x4. Let's first talk about the PixSim Lab Simulator board. This board contains a matrix keypad, LEDs, and LCD display, and a cooler heater with the buzzers, relays both, and a reset button for emergency cases. Now let's dump the code. As you can see, the system is on, the LCD displays the microwave is on. After startup, the system shows the different cooking modes such as micro, grill, convection, and start. These options are selected using the matrix keypad. Now I am selecting the micro mode by pressing the corresponding key, which is the one. As you can see, it shows the power 900 watt. Now the LCD asks me to set the cooking time in minutes and seconds. Using the keypad, I will enter the cooking time. If a wrong value is entered, we can clear it using the star key. Now let's put the some other value. Now I confirm the time by pressing the hash key to start cooking. Now the cooking process has started. You can see the countdown timer running on the LCD display showing the remaining time. I will now press the pause key. You can see the timer has stopped it, indicating the process is paused. Now I resume key to continue the cooking. The counter starts again from where it stopped. If I press the stop key, the cooking process ends and then the system returns to the main cooking mode screen. As you can see, it is back to square again. Start it again. When the timer reaches 0, the buzzer turns on to notify the cooking is completed. This simulates the alert sound in a real microwave oven. Now I will be demonstrating the convection mode. Here we first set the temperature. Let me give it as 45 and then confirm it. And now the system shows a preheating messages before asking for a cooking time. Now I'll be showing the start mode, which takes a predefined input of 30 seconds. This completes the demonstration of my microwave oven control system project, where user inputs are taken through a keypad, processed by the PIC microcontroller, and output is shown on the LCD with timer control. In the future, this system could include IoT connectivity, voice control, smart energy use, and improved safety monitoring. Learning outcomes of this internship. This internship helped me gain practical knowledge of embedded C, hardware interfacing, timers, interrupts, and real embedded system design. Conclusion. This internship gave me hands-on experience in embedded system and helped me understood how microcontrols controls in the real world appliances. Thank you for watching my presentation.